So far we were looking at the force that is required to stretch a spring, and we know in the case of a spring that force varies with the displacement. How about work done in propulsion? When you want to propel something from the surface of the earth into space. Now remember, in order to lift an object, the amount of force you need to apply is its weight. But if you take an object away from the surface of the earth, its weight is going to decrease. That means the force that you need to lift an object decreases as the altitude increases. And so, if you want to find the work done in propulsion, you must have an idea how the force decreases with distance. The force needed to lift an object depends on the altitude of the object. And according to Newton's law of gravitation, now Newton's law of gravitation says the force decreases inversely as the square of the distance. If r is the distance of an object from the center of the earth, then the force F needed to lift that object is given by F as a function of r equal to k over r squared, where r is the distance measured from the center of the earth. So, as you move away from the center of the earth, the force needed to lift an object is reduced, made smaller and smaller according to this relation, where k is a constant. Alright, now here k is a constant that can be determined from known information. For example, if you know a given altitude, and if you know the force that is needed to lift the object at that altitude, we can then find the value of k. We will do that as we go on in solving problems. Now, if an object is lifted from a distance r1 from the center of the earth to a distance r2 from the center of the earth, the work done is given by W equal to integral r1 to r2 of f dr. Now, let me take a minute to explain that a little more clearly. Let's imagine that this is the earth. This is the center of the earth. Now, we need to move an object, say, from the surface of the earth to somewhere here. Now, this is your r1. r1 is the initial distance of the initial position from the center of the earth. And this distance is r2. So we need to lift the object from a distance r1 to a distance r2. And you cannot use work done equal to force multiplied by displacement, because the force will keep on changing. Now, what is the nature of that force? We said that force equal to k over r squared. Now, what's the method we do? We take a small displacement dr here. We will assume that the displacement, during that displacement, this force will remain a constant. And therefore, the small work dw will be force times that small displacement. And force equal to k over r squared. So force multiplied by that small displacement is this. And all we need to do to calculate the total work done to move the object from the surface of the earth to the space station is the total work done will be integral r1 to r2 of this dw k over r squared dr. Now that's the method we are going to use in solving problems in this section. So the total work done to propel an object from a distance r1 to a distance r2 is given by integral r1 to r2 k over r squared dr, and that will be k k times integral 1 over r squared dr. Alright, how many of you can tell me what is integral 1 over r squared dr? Integral 1 over r squared dr. Now remember, the derivative of 1 over x with respect to x is negative 1 over x squared. Therefore, integral of 1 over x squared dx is negative 1 over x. Integral 1 over r squared dr is negative 1 over r. You can also do it using the power rule. 1 over r squared is r to the power of negative 2. Integral of r to the power of negative 2 dr is r to the power of negative 2 plus 1 over negative 2 plus 1. And that will be negative r to the power of negative 1, which is negative 1 over r. Now try that writing down on your own. So if an object is lifted from the surface of the earth, you see, if object is lifted from the surface of the earth, then this r1 will be the radius of the earth. And we will use the radius of the earth as 6.4 times 10 to the 6 meter. In other words, it is 6.4 million meter is the radius of the earth. Wherever we need that, we will use this value. Alright. Also, I told you earlier in this lesson that if an object has a mass m, the gravitational force on it by the earth is its weight. Force of gravity on an object of mass m is m times g, where g is the acceleration produced by the force of gravity, and its value is 9.8 meter per second squared. All this we talked about earlier. So, if a satellite has a mass of 2 metric tons, then the minimum force required to lift it is its weight. The minimum force that you require to lift a satellite of mass m equal to mg. So that m is 2 metric ton. A metric ton is 1,000 kilogram. So the 2 metric ton is 2,000 kilogram, and the g equal to 9.8 meter per second squared. Therefore, the total force necessary to lift this satellite off the ground is its mass times acceleration due to gravity. That is 19,600 Newton. You need a minimum force of 19,600 just to lift this satellite from the surface of the earth. That's right. This is the weight of the object. And to lift it upward, you need to apply an equal force upward. That's right. Okay, let's do a problem. Neglecting air resistance, determine the work done in propelling a 4 metric ton satellite to a height of 200 kilometers above the earth. And B, calculate the work done to propel it 400 kilometers above the earth. Well, if you can do this, then you can do that. The only thing is, replace your R2 by 200 kilometer here, and this is 400 kilometer above the earth. Alright, the force needed to lift a 4 metric ton satellite. Now, what is the force that you need to lift that satellite from the surface of the earth? Is equal to its weight, its mass times g, which is, mass is 4 metric tons, 4,000 kilogram. G is 9.8, so that will be 39,200 Newton. That is the minimum force you require to lift it off the ground. So, its weight is 39,200 Newton, means when the satellite is on the surface of the earth, its distance from the center of the earth. What is the distance of the satellite from the center of the earth when it is on the surface of the earth? It is the radius of the earth. and the radius of the Earth is 6.4 times 10 to the 6. This is your R1. Now what is your R2? R2 is 200 kilometers above the surface of the Earth. That means R2 will be this radius of the Earth plus this 200 kilometer. That's right. Now, using Newton's law, the force needed to lift this satellite, is actually an upward force equal to 39,200 Newton. And according to Newton's law, this force must be equal to K over R squared. And on the surface of the Earth, it is K over RE squared. That is, you see, the weight of the object on the surface of the Earth is this 39,200. Remember, this 39,200 is the weight of the satellite only on the surface of the Earth. As it is lifted away, its weight will be something less than that. So, when the distance equal to the radius of the Earth, the weight of the satellite is 39,200. We can use now these two values to find K. One more time, in this equation, F equal to K over R squared, when this R equal to the radius of the Earth, the force needed to lift that off the surface of the Earth is 39,200, the weight of it on the surface of the Earth. Therefore, what is K equal to? K equal to 39,200 multiplied by this number. That's a big number. 1.606 times 10 to the power of 18. And that is the value of K. Alright, we will now use this value of K to find the work done when the satellite is lifted from R equal to R1 to R equal to R2. Well, so we have these values. We know K. We know that the force that is needed to lift the satellite is of the form F equal to K over R squared. That means this force will change with this R. Well, using the value of K, we have F equal to 1.606 times 10 to the 18 divided by R squared. And we know this. The total work done to lift the satellite from a distance R1 to a distance R2 from the center of the Earth is integral R1 to R2 of FR dr. And we can now replace this F of R with this expression. That will be integral R1 to R2, 1.606 times 10 to the power of 18 divided by R squared dr. This is a constant, we can take it out. So the constant number comes out and you have integral R1 to R2 of 1 over R squared dr. Alright, what is R1? R1 is the distance of the surface of the Earth from its center, which is the radius of the Earth. And what is the radius of the Earth that we said we will be using? It will be 6.4 times 10 to the 6th meter. And what is R2? R2 is 200 kilometers above the Earth. That means the total distance is the radius of the Earth plus 200 kilometers. That's right. So R1 is the radius of the Earth and R2 is the radius of the Earth plus 200 kilometers. But of course you need to convert that 200 kilometer to meter. 200 kilometer is 2 times 10 to the power of 5 meter. Now add these two, you get 6.6 times 10 to the power of 6 meter is R2. So we can now replace R1 and R2 and we can perform this integration. Therefore the work done is 1.606 times 10 to the power of 18 integral 6.4 times 10 to the